I'm going to show how to find all the complex zeros for this polynomial function right here. And since the leading term here has an exponent of 4, there are going to be 4 complex zeros. Now, they could be all nice whole numbers, rational numbers. And if they are, then the graph will cross the x-axis 4 times. And looking at the graph, though, it only crosses twice. So it looks like there's going to be 2 real zeros, and then 2 of them are going to be complex zeros or imaginary numbers. And so to find those real ones, we're going to use the rational zeros theorem, where we're going to write those real zeros as a fraction. The top part of the fraction we're going to call p, and it has to be a factor of the constant term, so 168. And the bottom part we're calling q, and it has to be a factor of the leading coefficient of this term, the front term, and this coefficient is 1. So you need to list all the factors of 168, and the list is started right here. Plus or minus 1, plus or minus 2, plus or minus 3. All these numbers divide 168. And then you also need to list all the factors of 1, which that's easy. It's just plus or minus 1. And then create all the fractions that you can from taking one number from this list, it goes on top, and one number from this list, which there's only one number here, and it goes on bottom. So you have 1 over 1 plus or minus. So plus or minus 1's an option for the fraction. 2 over 1, so plus or minus 2 is an option. 3 over 1 plus or minus 3, and so on. So you get those list of possibilities, and you would want to check each of them to see if they are actually a zero. And you will check that by using synthetic division in the remainder theorem. But use your graphing calculator, use your knowledge that if it's a zero, that's where it crosses the x-axis. And you can just tell from this graph that it's going to be -7 and +2. And you can verify that then by actually using the synthetic division. But what I was saying is don't just check all the numbers from beginning to end. Maybe working a similar problem like this, you can't tell exactly where the zero is, but you could tell maybe that what it was close to by looking at the graph. And so then you would use the things on your list, start with the ones that are close to what you see on the graph. Yeah, so that'll speed you up if you actually look at the graph. So just to verify, I'll just walk through one of these. Synthetic division, proving that 2 is actually a zero. We list all the coefficients here. So 1, 5, -260, -168. And we're checking for 2 here. So you put a 2 in front, you bring down the first coefficient, and then you multiply 2 times that number that you brought down, and we write it up above, and then you add. So 5 plus 2 is 7. That's our next number we bring down, and we're repeating this process now. 2 times that 7, and we're going to write it up above. It gives us 14. Again, we add. 14 plus -2 is 12. Repeat the process. 2 times that's 24. Add. We get 84. 2 times that's 168. Add. And we get this, 0. So remember, this last answer here in synthetic division is our remainder, which a remainder of 0 proves that x minus 2 is a factor of our original polynomial. That's another way of saying, oops, wrong screen. That's another way of saying that 2 is a 0 of our polynomial. Alright, so you could do the same thing with a -7, and it would again come out with a remainder of 0. So what that gives us then is a way to factor down this polynomial to find the complex ones. And we actually do need to use -7. So I don't want to skip a step here. So we started with 2. We saw that it produced a remainder of 0, so that means x minus 2 is a factor, And here is what you would multiply it by to get the original polynomial. The leading term's 1, and then the next coefficient 7, 12, and 84, just like we have here. So since we started with degree 4, this one starts with degree 3, x to the third, 7x squared plus 12x plus 84. So we take that polynomial here, and we're going to divide it. We're going to divide it by x minus 7. We're going to check that negative 7 is 0 of that. So again, synthetic division, write down the coefficients, the negative 7 in front, and those same steps. Bring the 1 down, multiply it by negative 7, add them up. 0 times negative 7 is 0, add them up. 12 times negative 7 is negative 84, and we get another remainder of 0. So this is good news. What that shows us is how to factor even further. So this will factor to x plus 7, and the what it's multiplied by is 1x squared plus 0x plus 12. So again, we've just taken this and we factored it down further to right there. So now we have, again, just verification that 2 is a 0 of this, of our original polynomial. If you plugged a 2 in there, 2 minus 2 is 0. So f of x would equal 0. If you plug a negative 7 into this factor, you get negative 7 plus 7 is 0. So again, f of negative 7 equals 0. And there's no real number we can plug in here to make this factor equal 0, because you take any number and you square it, you always have a positive. You add 12 more to it, it's still positive. You can never make that equal to 0. But we're going to set it equal to 0 and use complex or imaginary numbers. So x squared plus 12 equals 0. That means x squared equals negative 12 if we subtract the 12 from both sides. And now take the square root of both sides. And they've skipped a little steps here, but you can write 12 as 4 times 3. So we have the square root of negative 12. We get rid of the negative part by just saying, by moving the I out front, because I squared is negative 1. And then 12 is 4 times 3. The square root of 4 is 2, so we can bring the 2 out. And then that leaves the 3 inside the square root. So we took the square root of both sides here, so to do that we have to have x equals plus or minus whatever the square root of this side is. So it's plus or minus 2i squared of 3. So those are our 4 complex zeros. 2 of them are nice looking numbers, negative 7 and 2, and the other 2 are complex numbers. And that coincides with what we saw with our graph. It crosses at negative 7 and 2, and then we have 2 complex zeros.